Hello and welcome to the Sentinel Innovation Center webinar. I'm Leslie Curtis from the Duke University School of Medicine, and I'll be moderating today's session. The U.S. Food and Drug Administration Sentinel system helps to address questions related to the safety and effectiveness of marketed medical products, and the Sentinel Innovation Center focuses specifically on developing innovative methods to further advance Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities through advanced analytics. We launched the webinar series to engage experts and innovators in key areas related to the Innovation Center's master plan. And with that, I'm pleased to introduce today's speaker, Dr. Michael Matheny. Dr. Matheny is an associate professor in the departments of biomedical informatics, medicine, and biostatistics at Vanderbilt University Medical Center. He is a practicing general internist and clinical informatician, and he co-directs the Center for Improving the Public's Health through Informatics. Dr. Matheny is an elected fellow of the American College of Physicians and the American College of Medical Informatics, and an elected member of the American Society for Clinical Investigation. His research foci are predictive analytics, data modeling, machine learning, and artificial intelligence, automated medical device surveillance, and natural language processing. The title of Dr. Matheny's presentation today is Overview, Considerations, and Challenges in Integrating Structured and Unstructured EHR Data into Common Data Models. Now, before we get started, I'd like to mention that your lines are muted. So if you'd like to pose a question, please do type it into the Zoom question and answer feature. I will be monitoring those, and we will answer questions at the end of Dr. Matheny's presentation. As you may have heard when you joined, this session is being recorded and will be made available through the Sentinel webpage, which can be found at sentinelinitiative.org. So with that, Michael, thank you so much for joining us, and I will turn it over to you.
Yeah, thank you for that kind introduction, Leslie, and thanks to the Sentinel Innovation Center Steering Committee for the opportunity to come and talk today. So really, I want this to be a slightly, hopefully a little bit less formal, more opportunity for questions at the end. The Sentinel IC has been asked to help leverage electronic health records for adverse event detection and medications and other activities. But one of those areas is really leveraging natural language processing, which has been a bit of a challenge in the field. And so I'm going to take a bit of time to go through some of the background on types and the use of natural language processing to set a level foundation for that. And then also talk a little bit about some of the common mature data models, and then dive into some of the challenges and issues that the use of natural language processing when you're in a distributed network face to help generate some of the conversation that we can have at the end of the conversation. So first, natural language processing. So, you know, it's funny, in some of my preparation for today, I went around trying to find a reference for what proportion of information content was concretely in free text versus structured data. There's been widely cited, you know, 70% of information content, 80% of information content, although it generally, when you look at the use cases, it's highly variable. I think this is a good example of that. Looking at a Norwegian sample across health centers, they found that in general, symptoms and disease mentions and and assessment and plans were very highly documented in electronic health record free text, whereas drugs and medications and surgical procedures were less common. And when you think about the use of free text, particularly narrative notes, where in general, it's to document care, to document sort of the plan of care, to communicate to other providers. You can see how this sort of information would naturally be present. And so when you think about trying to extract that information, it's really a bit challenging because of the abbreviations used, shorthand. A variety of different clinical disciplines have different nomenclatures for how they go about things. From a methods perspective, there really are sort of three large types of NLP. There's the historical rule-based systems, which build up a set of Boolean rules and process text strings to assess those. There's a hybrid approach, which uses rules and various aggregations to build clinical features, and then uses a machine learning model to then estimate the outputs for the NLP. And then there are those systems that are almost entirely machine learning in provenance. When you think about that, that's more of the interior of the method. However, today we'll be a lot more focused on the outputs. So when you think about that, you have a lot of natural language processing tools that really focus on a set of curated features. Examples for that might be if you're wanting to know infectious symptoms that are being reported in a primary care emergency room setting, if you need to know smoking history, if you need to know a family history of cancer. Those are all very focused tasks. There's another approach that says we want to try to process the entire document itself. And these sorts of tools like Medley, MetaMap, CTakes, Knowledge Map, and Clamp, and others really take a general approach to try to sort of map the entire document to controlled terminologies so that they're usable and computable. And lastly, and something that's been happening more recently, is really a set of NLP tools that themselves actually don't generate any mappings to structured data. They use Word to Vec, Doc to Vec, bag of words, and they generate a large set of features that they themselves aren't mapped to controlled terminology or clinical ontologies that I'll mention. So this is an example of a tool we used to detect infectious signs and symptoms presenting to the emergency room a number of years. And here you can see on the right an example of a tool that tries to go through and process all of the different text, map terms to clinical concepts. Red terms are actually negated. So in natural language processing generally likes to try to assert what the term is, and then in some cases try to negate it or positive assert it, and then in some cases map a relative time to that. So Hongfeng Liu and her group actually hasn't even come out in press yet. It's online only at JBI. Did a tremendous job of doing a systematic review of the literature from 2009 to 2019, looking at all the different types of natural language processing and how they played out. So if you look at on the left, you can see that still the majority of NLP tools are rule-based systems, although the rule and machine learning hybrids have a significant representation in the data. And then you have a group that's about a third that represents machine learning technologies. What I will say is that there was another clinical review in 2017 in which the vast majority were rule-based and only a few were machine learning based. In the last few years, we've seen the rise of much more robust deep learning and machine learning based systems for this. This also gives you a sense of where these NLP tools are being applied. Many are in a specific disease area, some are around clinical workflow optimization or drug-related studies, and then some of the subdomains that I won't go into. CN in this area represents clinical notes. So again, you see the majority of interest in the application of natural language processing is in processing progress notes, histories and physicals, with some other smaller pieces represented. So that article also did a review of some of the most recent best performances. So there are a number of annotated corpora that are released in the community that are used as reference standards for different algorithms to compete within. And what I think is really interesting to note is that many of these called annotation tasks or NLP challenges for a variety of different issues, medication problems, medications, named entity recognition, disease determination, template extraction. In many cases, the highest performing tools now are either a terminal hybrid of rule and machine learning or deep learning algorithms. So to transition, so you have these NLP tools, and traditionally, there's been a lot of work that's gone into develop them. However, the scalability and portability of these has really been challenged for a number of reasons. And so when we think about trying to adapt this to Sentinel and to distributed data network, you really have to take care in standardizing, harmonizing, aligning the outputs, aligning the tool use to try to make sure that you're as close to apples comparison that you can get. And there's a discussion in the informatics community around early binding versus late binding, in the sense that you could create a data lake and just use it for the particular use case that you want right at the point of use case, where you do the transformation all as you need. However, it's an extreme computation cost to do that. And when you're looking over a heterogeneous population of sites and networks with different computing capacities, the emphasis becomes more on efficient use of analytics, processing, transformation, and execution. And so for natural language processing, it's one of, particularly when using machine learning and deep learning technologies, are extremely computationally intensive. So pre-processing and extracting and transforming that data into a structured data representation is of tremendous benefit to large-scale mature data networks. So I'll transition from a brief overview of natural language processing over to common data models. And so when you look at common data models, I think it depends on how the common data model was initially funded and built, sort of what the early use cases and data representations are. Although if you look at the four mature common data models, I2B2 star, PCORnet, OMOP, and Sentinel, there's really been a lot of sort of convergent evolution because as each of these networks needs to adapt to more to broader use cases, more registry data, to electronic health record data, to publicly available data, you end up wrestling with some of similar issues across the different networks. So I just want to highlight here, particularly in the free text area, this is, however, one of the areas that is still sort of in the active wrestle state, for lack of a better word. I mean, there's been a challenge across all of these networks for how to store free text data, how to represent intermediate products, how to represent the outputs. And so that'll be the focus for the rest of the talk today. So I'm just going to do a brief overview without going into detail about some of these data models. I2B2 star really is centered around an observation fact. It doesn't have a specific representation for natural language processing for text notes or for the outputs of text notes, although it is very flexible in how you could represent that data. The challenge in that flexibility is that if you aren't very careful, it would be different. It would look different in one site than it would in another. I mean, there's no specific guidance around NLP or products of NLP. PCORnet also has a sort of a general fact table, but otherwise doesn't currently have specific provisioning for storage of notes or for NLP products. Sentinel, in the same vein, also has a variety of different observational data from administrative, clinical, registry, family linkage, mother-infant linkage, but to date doesn't have that NLP-focused data tables, and it's one of the interests. So the one mature data model that has done quite a bit of work in this area to date is the OMOP common data model, particularly around a domain for both the note and the NLP derived products for the note. And so what that data model stores is the patient information, provider information, linked encounter information, the type of event relative to the note. It tries to store a normalized version of the document title using the HL7 link ontology, and then it tracks the date time of the authorship. And so then the derived table for NLP products links to that source note, retains text strings around the NLP tag, tries to map the tag to a standardized control vocabulary, and then tries to identify the algorithm that built it, the date time of the actual concept, as well as the date time of the processing tool, and modifiers such as negation, and temporal terms such as past, present, and future. I wouldn't, a primer on the common data models for the conversation wouldn't be complete without the harmonization project. So this is a project that the FDA led with a number of government agencies that attempt to sort of build cross mappings using a FHIR framework to allow portals and queries to basically be usable across different data models. And so since this is beyond scope for the call. I won't go into more detail here, but it's important that when we talk about mapping natural language processing and NLP products to one data model, it's something that all of these mature data models are going to face. And if there's ever need to sort of query across data models, then that's something that that a harmonization project would have to face as well. So some of the challenges. So there are really five major categories of challenges when trying to standardize the NLP outputs. So I'll try to sort of go over them in summary and then dive down into a bit of the pieces. So first, there's relevance. So many NLP tasks don't need or want all of the text. Not only is it computationally expensive, there's also relevance issues. Some of the documents are really low information content. Some of them could be active noise to the use case, and so relevance is an issue when trying to represent these. Standardization is also a key issue. So in order to try to run a query using the output of natural language processing in multiple sites, you have to try to represent your data in a standardized way. Veracity or accuracy. So is an 80% F measure or 80% accuracy sufficient for the task? Is 90%? How to represent and actually manage differential accuracy and performance in different tools is important. Portability. So there was a prior Sentinel presentation that looked at how to adapt features from one site to another site using cross mappings of administrative codes. That issue is present just as strongly in NLP. Practices around documentation, policies in place at the institutions all represent drift in how data are represented in different text corpus sets. And lastly, provenance. So, you know, a distributed network really has to make a decision around how detailed and how organized the provenance of the source and transformation are for their network. So at a base level, you want to be able to store the note content, the metadata, author and co-signer, which I think is sometimes missed in academic institutions and in practice extenders such as nurse practitioners or physician assistants. Many of them have a co-signer or an attending signer, and not having both of those pieces of information can sometimes damage the provenance of the information. So one of the first issues is related to relevance. So if you're going to try to filter out some of the documents for any particular NLP task, you have to actually know what you're trying to filter out. There's been a large effort underway to build a LOINC document ontology with 5 separate categories so that you know whether it's like inpatient or outpatient, EHR, sort of the setting, what the service is that's doing it, surgery, medicine, the role of the person. Is it a medical student? Is it an attending? Is it a resident? And then the kind of document. Is it a discharge summary? Is it a history and physical? Is it a primary care note? So unfortunately, while those standards exist and have a fair level of comprehensiveness, there's been some informatics articles looking at sort of comprehensiveness of these axes. In most electronic health records, it's under-specified and under-mapped. So there's, while only in this one example in New York, and there's similar data in the VA, while only 8% had no access, very few had 3 or 4 of these, which makes filtering and sorting and selecting documents to process and use more challenging. So I want to take a little bit of a side note to note that this is actually a really good opportunity for a noisy labeling task, meaning since these documents have some of the documents have each of those 5 axes labeled, you can use machine learning to actually use a pipeline, train a machine learning algorithm on the document axes, and then apply it. So this is a study that we did doing a similar data quality augmentation that Sheridan Parr led, but looking at laboratory testing. So using the LOINC tests where you have noisy labeling of LOINC mappings for laboratory data. These tools, deep learning, machine learning tools, really have been effective in augmenting data quality. And so I think this is one of the areas that really each site in a distributed network could deploy to help augment the identification of the types of the documents that they have in their storage. So next is standardization of NLP outputs, and this may be a point of discussion for the group, but I would say really if you're operating in a large distributed data network, you really can't use some of the NLP tools that really try to represent features without mapping them to a controlled ontology. So examples of that would be, word to vec, doc to vec, bag of words, things that represent things as string tokens but don't really attach clinical meaning to them. So just to sort of to highlight, there are many ontologies that exist, and so when you're actually designing which ontologies you're going to require or recommend for use in your network, I think it's important to standardize those as well. Many of these generally have leading vocabularies for each, like LOINC for labs, RxNorm for medications. But I still think it's important for a distributed network to specify these up front, or otherwise you run the risk of different data partners choosing different standards, or moving forward the standards that exist within their electronic health record that may not necessarily be as widely used. So some of the key issues that I just really want to bring up as significant issues for mapping. So one, there's an ongoing discussion in the community about whether to take NLP outputs and store them in their own separate table, like the OMOP community has done, or if you have enough veracity and enough accuracy, do you actually store condition? So if you're mapping these to say a vocabulary like ICD-9 or SNOMED, do you actually store these with other facts in the same area, like conditions or procedures? The problem is the provenance of that is differential, meaning the amount of information content in an actual administrative code from a discharge or from a primary care visit is not analogous to an NLP term extracted from free text. And so how you handle the provenance and the veracity and the differential information content between those types is really important to handle in a data model. The other thing is the threshold of the accuracy. So if you have a tool that's only predicting a mapping at a 60% accuracy or 70% accuracy or F measure, at what point do you actually allow those products to be used in an analysis process? Another issue in NLP text in particular is temporality. So while a note may have been developed on January 3rd, 2019, it may have talked about a heart attack that happened 3 weeks before, so relative to that. So dealing with relative time inside a document for some particular tasks is not an issue, but for others can be very important in order to reduce the level of noise. And it's a hard NLP task. And then the other one is negated terms. So there's been, in one of our research projects in particular, there was a big discussion around whether a negated term, which has information content, should be separately documented, processed, and stored, or whether you ignore them. And I think, given that coverage for negated terms in many of these control vocabularies is poor, and that brings up an issue of coverage. So I want to sort of take you out of the abstract and into the concrete. So one of our projects was a research project to develop a risk prediction model for readmission, and really to use natural language processing to augment structured data to see if we could get a better performance score than some of the traditional tools, which have been like in the 0.65 area and the receiver operating characteristic curve. And so we developed a curated set of terms, and then used a tool developed by Wendy Chapman and adapted it to these tasks. But one of the things that we needed to do, since we were actually trying to port this tool to other institutions So this is at Vanderbilt, and then we ported it to Dartmouth and University of Utah, was to actually try to map all of the data to OMOP, and then actually try to use the OMOP note NLP and note targeted domains. So it turns out when you're actually trying to take a curated set of clinical information where you actually are ascertaining negation as well as particular elements, the coverage in these controlled terminologies is not always present. So there really wasn't a good coverage for instrumental support, for example. And then the other issue that you run into when you're dealing with natural language processing data is overlap with structured data that already exists. So if you start incorporating structured data and unstructured data where there's collinearity or strong associations between the data, you have to handle that in your downstream analyses depending on the use case. So then the other issues I mentioned is veracity. So how accurate is accurate enough? So in many cases, if you don't know the denominator, if you're trying to extract individual elements from a document, you need to use F measure, and you have to sort of determine positive predictive value and specificity there. In other cases, it's sensitivity and specificity for document or patient level cases. Usually these require a silver or gold standard to evaluate on, whether that's some annotated group, which is costly to perform, or a noisy label from other structured data. Unfortunately, because of drift that occurs between NLP algorithms, that can be an issue. And then storage and reference retention of the performance is also important, and how much you store is an issue. So this is another example from one of our prior projects where we were trying to extract risk factors relative to acute kidney injury for a variety of different things. So some of them were highly represented in structured data, and some of them were almost never represented in structured data. So for the drug exposures, this is an example of how you would basically assess the data elements that you're getting out of your targeted NLP task. And if you look on the very right-hand side at the F measure, one being the best possible, and as you can see, the F measure, for some, we elected to retain in our downstream analytic processes. Some we did and some we didn't, and then others were just simply not performing well enough to be considered in many cases because the instances were extremely rare. And so I think when you're using these tools, having access to this sort of data, not only in the reference population that the tool was developed, but in your local environment of application is critical for being able to use these tools with a reasonable amount of accuracy. So another issue that distributed data networks face is sort of what level of intermediate products to retain and store. So that includes, do you store the text strings? Do you store the content around the text? Do you need to store the algorithm? Do you need to store the what version the algorithm was? Do you need to store the coefficients in the internal matrices or beta coefficients or forest trees? Some of that is very difficult to do in any sort of queryable way. And so those are active issues for the use and standardization of these tools. So I want to highlight local updating. So this is an article that was done a few years ago looking at ascertainment of asthma and some asthma symptoms. It was looked at a tool that was developed at Mayo, and then they applied it. And as you can see here, when you apply that in another location, Sanford, you have an initial drop in performance. And then they actually had to refine the algorithm with additional training labels and rules in order to try to reapproximate the performance of the tool. And we also have a project that unfortunately I couldn't show today because of unpublished data, in which we're showing that the algorithms we built for the prior project in instrumental support and for readmission are actually experienced similar drops in performance when ported to Dartmouth, and then had to be retrained, as well as Utah. So each had to have a separate individual retraining process. So lastly, I want to say that when we're talking about natural language processing and how to make decisions at a network level around how to represent that in a common data model, you want to think ahead to other use cases. So, one of the things that the Sentinel Innovation Center really wants to do is do probabilistic phenotyping and representations for derived data facts. And so some of the same issues exist here. And so I really considering them all together and how you would represent that is a good example. This is a work that Gigi Kula and our group did where we were developing a probabilistic phenotype around hepatorenal syndrome. And a lot of the same technologies are in play here. You have extraction of clinical data, you have processing from a generalized natural language processing, you do dimensionality reduction and data transformation of your products. And so you could conceptualize where you might have an NLP part that then drops into a common data model, and then another algorithm, a phenotyping algorithm that would pick up the data from the common data model that would be the NLP outputs, and then process it through a different algorithm to probabilistically assign a likelihood of a given clinical condition or phenotype. Those also need storage, provenance, accuracy, performance. And so this is a generalized problem, not just specific for NLP text outputs. And so in conclusion, so I hope that I made a good case that NLP outputs are highly valuable. They're necessary to sort of leverage some of the pieces of electronic health records in practice. There's tremendous opportunity in them. In order to really scale out to a large distributed network, there has to be some way to represent these outputs in standardized formats and patterns so that you can then execute queries and systems on top of them. But there's a lot of challenges in that. There's how they get represented in a common data model, what controlled ontologies are used, where do you put the outputs, how do you maintain accuracy and veracity of those outputs, how do you maintain provenance back to the source data, and then it's critical to think about other derived data products from a base common data model, such as probabilistic phenotyping when you're considering these things. And so I think that is it. I wanted to leave plenty of time for questions, and so I'm happy to go from there. Thank you.
Excellent. Michael, thank you. That was really a terrific presentation. And as you mentioned, we're now going to open the question and answer portion of the webinar. Just a reminder to everyone who's joined us today, your lines are muted. So if you have a question, please do type it in the Q&A panel, and I'll work on that list as it materializes. So maybe let's start with a question from Kevin Johnson. And his question, of course, there are other data models, and he references the US CDI model. How does that compare to the 4 models that you presented early on or that you touched on?
Let me see if I can. Oh, I'm not muted. I mean, I think that's an excellent example. I mean, it's definitely one of the useful models. I think it really depends on how these things were originally built. So Sentinel was originally built as pharmacoepi surveillance. Coronet was originally built for electronic health record derivation. OMOP was also built for pharmacoepi processes, and so certainly those models, CDI model, would also be usable for a wide variety of use cases.
Yeah, and you made that point nicely during your presentation. I mean, common data models originate for specific purposes, right? And so kind of keeping that in mind is really important. We have another question related to bias and underrepresentativeness that certainly we've read and heard a lot about how natural language processing can sometimes, because it's relying on the data that are in the electronic health record, sometimes there are implicit or other biases that find their way then into structured data when we're using natural language processing and machine learning, of course. Can you touch on that and maybe talk about strategies that are currently in place to mitigate that, or how do you approach that?
Yeah, no, I mean that's an excellent question, and one that we've been facing. A lot of the risk prediction algorithms that have been coming out of the artificial intelligence community have really had some high profile bias issues, and so I think for natural language processing it's also an issue. um, I think it's important to understand the context of how documents are created. So if you have a cardiac cath or surgical operative note, primarily, the way you consider that is that they're there to basically document for medical legal purposes the process that took place, all of the things that happened to the patient, and devices that were implanted, and surgical approaches that reduce any complications. And so you could expect that it to be thorough in that axis, but maybe very underrepresented in other axis. And I think almost all clinical documentation is going to be that way. The computer science community has developed some algorithms to try to help assess bias, although it's really challenging in the document context because you have so many layers of processing from the raw source text strings out to the output that's a challenging task.
Yeah, no, but that is a really, I thought it was a great question and a
Yeah, it
really
is.
challenging, really challenging to address. I had a couple of thoughts as you were presenting as well, and you talked about the importance of veracity, and I really liked that example that you showed of the kinds of information that institutions, that organizations should have to make sure that their algorithms, what they're doing with the natural language processing, is actually generating accurate information. How should we be thinking about what I'll call the durability of those internal estimates of veracity? And I say that, all of us are in this now peri-COVID, in the COVID era. And I think about how very many things are changing in terms of the way healthcare is delivered as a result of this. And I, as a data person, immediately go back to how will that fundamentally change the way that data are represented in electronic health records, and how should we be thinking about how often do we need to make sure that these approaches that we're using are still generating accurate information? Does that make sense?
Oh, it makes perfect, and it's it's an excellent question. So I think that's actually true for data science as a whole. So it's true for structured ICD-9 data. It's true for it's true for lab data if you change your assays or you change the technique at which it's true for natural. So I think really never presuming that always presuming that data are dynamic, that they're changing over time, and that approaches to surveillance and detection of drift are really critical for risk prediction models, for natural language processing tools, and I think for data networks like Sentinel and the others, I think it's critical to put into, essentially it's like a data quality process where you're routinely assessing drift. And as far as how often, I don't think anyone knows, or perhaps a better way to ask that is it's very differential on the context of the data being generated. So some data may be stable for years and others, may drift very quickly. Although, as we've seen, COVID created such a stark sort of shift point in how clinical care was delivered, and how things were documented, and many corners were cut and documentation was stopped here and started there, that many algorithms broke across the system. Not just NLP prediction models, and so some things you can't anticipate, but I think there are algorithms and tools that need to be in place to help us prevent using these tools when they're no longer accurate.
Yeah, that's a great bit of advice. So let's go back to this issue of temporality.
Mm.
And as Jeff Brown notes, in medical product safety, the order of events is critical, as is the identification of incident versus prevalent conditions. You mentioned that the EHR data might not have the clinical onset date. is it possible to use NLP and with an EHR to identify true incident event that occurred, within a certain number of days of an index date? Or how do you think about that?
Yeah, no, I think that's a great question. There's a whole subdiscipline of natural language processing that deals particularly around the temporality assignment and trying to basically use a sequence of notes within a single patient to then try to order all of the occurrences of symptoms, disease onset, and it's a pretty complex field, and one I think that still has a lot of opportunity for growth and innovation. And so because a lot of the data in a lot of the text mentions in NLP are relative date, not absolute date. So yeah, doc, I had, the chest pains about 3 weeks ago, but then if you go back, then you have a number of biases, recall bias and other things that are operating. So if you go back 3 weeks, then, the patient may have been seen then and said, hey, well, I've had it about 2 weeks. So then you actually have conflicting information and text notes across time that you have to try to disambiguate and merge. But it's a really fascinating area of natural language processing, and one that still has a long way to go.
Yeah, I think you're highlighting too, and you did throughout your talk, that what I view as just the enormous potential for natural language processing in the work of Sentinel, and at the same time the real work that is yet to be done, or that's being done across many disciplines to figure out how best to implement it. I really appreciated your list of key challenges associated with implementation. And, I think they included, how the data are represented in the common data model, where you put those outputs, whether they're embedded or separate. We talked a little bit about updating algorithms for the local environment. Of those challenges, which ones, which ones do you see that we're making sort of best progress on? Which ones, or maybe for us in the Sentinel Innovation Center, which ones do we really need to sort of focus on in the near term in order to leverage these approaches in the near term and intermediate term? It's kind of a convoluted question, but I'd love to kind of get your sense of that.
Yeah, it's a good question. I feel like the standardization process, the actual mapping of text strings to controlled terminologies, is probably the farthest along. I feel like some of the issues around portability are sort of the next order of difficulty, because then you're dealing with differential data drift, and then there are multiple approaches to that. I mean, do you adapt the feature vector or the features underneath the NLP so that they mean the same thing at different sites? And there's a group even in Sentinel that's actively working on that. Or do you take the actual algorithm itself and update the coefficients or the actual algorithm in order to be able to pivot to a different data representation? So that's sort of the next layer up. And then I feel like issues of scalability and sort of managing the data over time and the accuracy over time. So there's one, just porting it into another environment, and then there's maintaining it over time, and that's even more challenging. So I feel like those are certainly the biggest issues.
Yeah, and the portability piece, I would say, certainly maybe 3 to 5 years ago, that was a piece that didn't seem to be getting nearly enough attention, right? And as often happens, as we try to deploy tools or use the awesome things that other people have developed, we realize that their awesomeness may not translate to our environment. And as you said, that's a real issue in a distributed network. So I'm glad that you focused on that. I had not seen the paper that you shared by I think Sun Yang Fu. Is that correct?
Yeah, you mean the systematic review?
Yeah.
It was really an awesome read.
I can't wait to read it. But I was struck as I looked at that beautiful graphic. Talk a little bit, or maybe share your opinion about where the NLP I'll ask this just in the vernacular, where the NLP juice is most worth the squeeze, right? From a Sentinel medical product safety perspective. I think you did, I'll say a little bit more while you're thinking about your answer to that. I think you did a really excellent job articulating what some of the challenges are. And I'd love, does this give us some indication where people are actually using it, of where it could be helpful for Sentinel? What are your thoughts?
Yeah, no, that's a good question. So I was actually heartened to see that, there's a lot of work around disease and drug related and adverse event related studies. And so, I think if you, I thought it was a great graphic as well. And so I think there's more work to be done using some of the more modern techniques in this area. So if you look at the slice that are deep learning and machine learning, which are sort of proven in just recent years to be some of the most robust. I think there's definitely more work to be done around the drug-related adverse event access and medication extraction stuff. So I would say it bodes well for Sentinel's use of natural language processing, because certainly this is an area of focus that's widely acknowledged to be important, and so it's not a ground zero or a greenfield environment. So I think there's plenty of tools and applications and interest to help leverage and develop a best practice in the Sentinel network.
Great. So, maybe, I know we have time for a few more questions, and I really appreciated the emphasis that you gave to provenance, and really the whole kind of transparency and importance for understanding the reproducibility of the natural language processing approaches. That's, of course, a really an even more important issue these days, maybe than it was even 6 months ago, and it was pretty important then. It sounds, my takeaways from your talk are that, how we store these data matters a lot, because some models allow us to store a lot more information that would allow us to sort of back into, if you will, source data, right, in an easier way. Talk a little bit, if you will, though, about generally speaking, the thinking around transparency, if you will, in natural language processing. And so the perception, much like with machine learning, is that there can be a bit of a black box, but there's a lot of nuance in going from free text into structured data. How has the thinking within the natural language processing community sort of evolved in that respect?
So just to make sure that I understand, so you mean sort of what level of provenance and what level of sort of intermediate products from the source to the final sort of mapped result are necessary and really warranted in order to engender trust in the use of the tool? Is that a fair?
Yes, that is.
Okay. So I think particularly super users and those that want to do sort of the quality assessment and sort of surveillance of the tool really as a community seem to want the intermediate product layer, which is sort of what were the actual text strings of note, what was the what was the text context around those, and then and then the other issue there is sort of maintaining some reference standards. So we haven't even I briefly mentioned it, but then so if you have 5 sites that you're deploying an NLP tool to, and you need to get performance estimates for all 5 sites, do you need to do a chart review of 50 documents in order to, is that enough? Or do you rely on a noisy label from a structured data proxy, knowing though that in most cases that if you had a good structured data proxy, you wouldn't need the natural language process to begin with. And so, I think ways to cheaply build sort of surveillance and reference standard and data quality checks, and then having those intermediate sort of raw, I would say raw process is how I would call that, where you have the document broken down into very small chunks of vectors and word strings, will help quite a bit.
Yeah, that makes a lot of sense. Thank you. Um, so could you talk a little bit about, this is in the area of algorithm refinement, how much work is generally involved in that, and how does it compare to just starting from scratch in a new environment and building a new algorithm? You know, what are the advantages of my borrowing from you versus me just starting de novo?
Yeah, I know that's an excellent question. And I feel I'm going to pull in a little bit from the risk modeling literature here as well, which is sometimes when you build machine learning algorithms are traditionally fairly data hungry and take a number of training samples to really achieve stability. And so in the modeling literature, there's been numerous examples where updating a previously existing algorithm when you have a smaller sample size in your deployment environment tends to result in a better performance, a better sort of locally achieved performance, because you're still able to leverage a lot of the information content from the larger external training data. But certainly, you're right that that when you get to a certain scale, then developing a locally developed tool sort of eventually remodeling overpowers updating or adaptation. I would say though, there's an issue that I didn't explicitly bring up, which is when you have to be really careful when you're developing a different tool instead of adapting the same tool, that you're actually getting the output that means even a similar thing to what you did in the original tool. So, do the clinical concept maps actually line up from a content perspective? Because there's a risk when you build a completely new tool that you're completely apples and oranges.
Yeah, that's a great point. Um, so we have a longer question here from Jeff Brown, and I'll read it for everyone to hear, but just warning you that you'll be hearing me read for just a little bit. So Jeff says, Sentinel has long struggled with adding domains to the data model without a specific use case and partners who can implement, right? Need to have a reason to use it and people who can do it. So it's easy to add a table to the data model. It's a lot harder to populate it every few months and way harder to standardize across 20 plus partners to support on-demand distributed analytics. So any lessons from other networks, VA, other organizations that you've worked within about how you would actually design or think about implementation within the Sentinel context? So do you do the NLP and extract every ETL? Is it project specific use, data on demand? How do you think about the way forward for NLP in the Sentinel context?
Yeah, no, that's an awesome question and a tough one. I guess I think the most success from populating these data models tends to happen when it's developed in the context of a use case. And I think the Sentinel IC will have an opportunity in the next year or two to have some active use cases with natural language processing products to think about how multiple sites could represent that data. But generally, these are iterative. And I agree with you. Tables are easy to model and then hard to maintain. I would say for NLP, you're not going to be able to have a generalized tool that's processed on every node across the enterprise and maintained in real time. And I mean, the computational infrastructure required for that is just way out of reach for most partners. And I don't know that it's necessary. I mean, if you have use cases where you really are focused around medication adverse events, then it might be that some subtypes of documents or certain mappings to certain controlled terminologies are really where you want to focus your effort first. Try to make lighter weight tools. Maybe they're not the most sophisticated from a machine learning method. Maybe they don't use deep learning. Maybe they use a different method that's maybe 5% or 10% less accurate, but 20 times cheaper to implement and maintain? And these are all questions that distributed networks will have to face as we try to really scale this out.
That was a great answer to a really tough question, Michael. And I like that you brought that back to the Innovation Center. And I think the real opportunity that we'll have over the coming year to articulate what that plan forward might be. So, we're really at the end of our hour, and I just want to thank you again for presenting today's webinar. It really was excellent, and I appreciate the level of detail and the clarity of the challenges that you identified. As a reminder to everyone who's joined us today, the session has been recorded and will be made available through the Sentinel webpage. You can also find details and a registrations link for future Innovation Center webinars on the website, which again is sentinelinitiative.org. This concludes our session. Again, thank you to Michael for a great talk, and we hope to see all of you again next time.
Thank you very much, Leslie. And